How's it going, everybody? So today we're going to be talking about a new parent function called the rational function, and we always start off with talking about how we move these various parent functions around on the graph by looking at their transformations. Now, we're only looking at a couple of transformations for a rational function because it is unique and a little different. First and foremost, when looking at this parent function, it had a horizontal asymptote as well as a vertical asymptote, and it only existed inside these little quadrants right here. Okay? And so the idea, ladies and gentlemen, is that when we apply these transformations, believe it or not, we're actually going to be more heavily concerned with how these transformations move the asymptotes more so than the graph itself, okay? The idea for when we do graph these parent functions, we want to be very precise on the asymptotes and the location of them, but we want to be just kind of accurate with the graph, okay? Now, of course, the parent function, if you're curious, is this guy right here. F of x is equal to 1 over x, okay? And the various transformations that we're going to be looking at, like I said, was a couple. We're going to be looking at a vertical stretch, okay? We're going to then be looking at a reflection across the x-axis if the negative's in the front, right? Reflection, x-axis. And then the h value actually talks about how we shift things left and right still, okay? So this talks about going left or right, as well as the location of the vertical asymptote. So the vertical asymptote. And then, of course, the k value is what tells us we're going up or down, but tells us the location of the horizontal asymptote. Okay, so let's go ahead and take a look at this in the examples down here and how we're going to do it. So you'll be given these equations where you will have to perform some synthetic division on. And just as a reminder, the way you do it is you create your upside down little or obelisk, or you create your little L, and you're only putting in your coefficients. So you have your 4 and then your -5. And then on the outside, the divisor, but remember it's the opposite. So instead of -3, you put +3. You bring down your first term, and then you do 3 times 4, that's 12. Put that there, and then do -5 plus 12, and that's going to be your 7. Now, when you write your answer, you're going to kind of write it backwards, and that seems weird, but we're going to write it backwards because that way we can look at all the transformations. And so the idea is typically the way you would write this would have been a 4 plus your 7 over x minus 3. But because I want to see the transformations, I'm going to write it as 7 over x minus 3 and then my plus 4, okay? Now, of course, what we're looking at here is, and I'll go ahead and box this in because this is what I'm looking for after you do that. We're looking at a stretch, okay? A vertical stretch of 7. We have an x minus 3. That tells us the location of our vertical asymptote, right? And then the plus 4 is telling us the location of our horizontal asymptote. So the idea is that we went to the right 3 and we went up 4. And so when you go over here to talk about that, so since we went to the right 3, that means the location of my vertical asymptote is now at x equals 3, and my horizontal is at y equals 4. Remember, x equals represents a vertical line, y equals creates a horizontal line, okay? Just a reminder. Now, because of that, we have my, and I'll try to use the same colors, that x equals 3 because we went to the right 3. We went up 4, and what color did I use? I think I used red, yeah. So we'll use red again. So just like that. And so now we'll go ahead and, for the most part, draw an accurate sketch of where the graph should be. And he'll still be in the same quadrants, okay? Just like this. The biggest thing is making sure that you have your asymptotes where they need to be. Now, when it comes to talking about the domain and range, you can use simple set builder notation to kind of describe it. So for the domain, what you can say is x is such that x cannot equal 3. And what that is telling the reader is that x can be everything else, but it just can't be 3. And then you can also say for the range, very much the same thing. You can say that y is such that y can't be 4. okay? And the reason for that, remember, is due to the asymptotes. Remember, asymptotes are things you can get extremely close to, but you can never cross or touch. And so that's what we say there. Now, you might see some union notation. That's a little bit more, I guess, involving interval. And the way that you could describe it utilizing the interval notation with the union is you could say that this graph goes from negative infinity to 3, union 3 to positive infinity, okay? And then you could do the same thing for the y. You could say that this graph goes from negative infinity but to 4, union, and then 4 to positive infinity, okay? And the reason for that, if you really look at the graph, this piece of the graph towards the domain is going towards negative infinity, but then gets stopped at the asymptote, but then picks back up. And then the same thing with the horizontal when it's kind of talking about the range. Now, if you need a little bit more than that, definitely tune in for the live session, and we'll go into much more detail if need be, okay? So that's kind of what we're looking for. Now let's do number 2, just to kind of reiterate what we're supposed to do. So the idea is we create our synthetic division process. We have a 2 and then a 4. The 4 on the bottom goes on the outside but is negative. Bring down your 2. Negative 4 times 2 is negative 8. 4 plus negative 8 is negative 4. And we write it backwards, okay? So you've got your negative 4 over your x plus 4. And then you've got your plus 2, okay? Now looking at this right here, what I see is I have a vertical stretch of 4. So I have my vertical stretch. But I also see that negative in the front, which is a reflection, okay, across the x-axis, right? And I'll show you what that's going to do. And then the plus 2, or actually, let's do with the plus 4. The plus 4 is telling us that we're going to the left 4 units, but then the plus 2 is telling us we're going to be going up 2. Now, this right here, okay, is going to be let's start off with the asymptotes, okay? So we went to the left 4, so that's going to adjust my vertical. And so 1, 2, 3, and 4, I'm right here. And then I did go up 2, so let's go up 2, 1, 2. Now, what that's going to do, because I have a reflection across the x-axis, the line that used to be right here, okay, that I'm kind of drawing as a dashed line, okay, and the line that used to be here, they're going to reflect across and now exist here, okay? They're basically going to flip to the other side. Now, the vertical asymptote is going to be x is equal to your negative 4. And then over here, your horizontal was your y equals 2. And there you go. Now, you can go ahead and shorthand the domain again. You could go ahead and say that the domain is x is such that x cannot equal negative 4. And you could say for the range that y is such that y can't equal 2. Now, you could also do the interval one where you have, it goes from negative infinity to the value of negative 4. And then from negative 4, oh, forgot my union. And then from negative 4 to positive infinity. And then for the range, you would say from negative infinity to 2, union from 2 to positive infinity. And there you go, guys. And so that's how you would utilize and describe the transformations of a rational function. If you have any questions, guys, definitely tune into the live session, like I said. But here's the basics, so that way you can definitely work on the Wiser Me assignment. Thank you guys for your time, and let me know if you need anything.